Before I start anything? I'm sure it'll come up as we go. So far we focused on spatial dependence. We reviewed spatial autocorrelation, global test statistics, local test statistics for spatial autocorrelation, different ways in which to specify spatial dependence in a regression model, spatial stochastic processes, autoregressive, moving average. And then yesterday we went specifically into the test statistics for spatial autocorrelation based on regression residuals, and then the estimation of the spatial lag and the spatial error model by means of maximum likelihood techniques. And now we're shifting gears, so to speak, not totally, but we will focus our attention on spatial heterogeneity. And as I mentioned the first day, one of the challenges in applied work and empirical work is to separate out heterogeneity from dependence. They often occur together without strong theoretical priors or a lot of structure in the model. It's often an identification problem, and it's very difficult to tease them apart. And what I'd like to do today, and there's a little less material so we have some more time later on for the presentations, is I want to focus on two ways to view spatial heterogeneity. One is what I call discrete heterogeneity, and you can think of this as kind of a fixed effects approach to modeling heterogeneity. The other one I call continuous spatial heterogeneity, which is not quite a random effects, but it is more flexible in some sense than a fixed effects approach. And so we'll start by going over some concepts and then some specific techniques on how to deal with discrete spatial heterogeneity. And these are pretty straightforward things, but very powerful in providing insight into structural shifts in the data and the potential need to adjust your model to actually deal with these structural changes. The underlying driver for this is that a very strong assumption, requirement for cross-sectional spatial data analysis is this spatial stationarity that we've talked about a couple of times now. And of course, a structural break or structural change violates spatial stationarity. So then our approach is the same as always. We try to model the structural break, and then after we've done that, in whatever fashion, what remains satisfies the stationarity assumption in the sense that it is more or less uniform, constant mean, constant variance, and so on. So let's focus and outline specifically what we mean by spatial heterogeneity. It's really about a different perspective on how we analyze data. The global perspective is couched in a need to look for overall equilibrium. A single equilibrium, all the relationships that we estimate are constant. So we have a single set of coefficients for the whole data set. We have constant variance. We have constant functional form. The functional form doesn't change. That's the traditional perspective, and in some sense, it's an ideal. The ideal of scientific explanation is to come up with simple rules, or as they used to be called, laws, that explain a lot of phenomena in an incredibly parsimonious way. That's the ideal. In practice of empirical work, we often encounter situations where this doesn't really hold. And the other perspective then is a local perspective where the focus is on the possibility of multiple equilibria, the possibility of non-stationarity, the focus actually on non-stationarity, on the variability of the parameters, the variability of the functional form. And there's really two aspects to this. One is a fix-it approach, is to control for the variability. Another one is much more challenging and much more difficult, is to actually model the variability. And it's a simple example is if you find that your model, and there's several examples of this in empirical work, that the model, say, for counties in the US doesn't fit the South, you stick in a dummy variable for the South. This is what I call a fix-it approach. It fixes the problem, but it doesn't explain anything. The dummy variable by itself does not provide an explanation for why your model does not do well in southern counties. There's another classic example in empirical work, it's Appalachia. If you estimate models and Appalachia is part of it, very often the model doesn't fit well there either, and a lot of people have solved this problem by sticking in a dummy variable. And again, it fixes the problem, it doesn't explain anything. So what we'll see today is mostly fix-it approaches, because the actual explanation is very difficult and often requires more information than we actually have. And that is the challenge in dealing with structural variability or with non-stationarity. It's one thing to fix it so that our remaining disturbance terms or error terms satisfy the standard assumptions. It's another one to understand why a phenomenon is different in different subsets of the landscape, if you wish. Homogeneity, just to set the stage, the model is the same everywhere, the parameters are the same everywhere. So if we put this in the context of a regression model, we have observations at locations I for the dependent variable y. We have matching observations for the explanatory variables x, a fixed set of coefficients beta, and an error term. And the bottom line is beta doesn't change. The error term ideally is IID, identically and independently distributed, and a constant variance. The opposite is extreme, what I call extreme heterogeneity, where everything is different everywhere. Now, as we very quickly realized, that's not a workable situation. But it is a useful conceptual point of departure, in that here we have a situation where we conceive of the parameter beta indexed by location I. In other words, every observation has a different parameter. And this is referred to as an incidental parameter problem, namely because every observation has its own parameter, as we get more observations, we don't gain any information, but we only get more parameters. And so this is a situation where asymptotics actually doesn't help, because as you get larger and larger data sets, you get more and more and more of these individual parameters to estimate. And this is something that creeps up on you in some models if you don't, if you're not careful. For example, the heteroscedastic model of where the white variance estimator is used. A lot of times when students look at this the first time, they say, oh, we're estimating a different variance for each observation. Well, you actually don't. That's impossible. That's never going to work, because you cannot estimate a parameter with a single observation. So what you do, in fact, is use some tricks. And the white trick is that you're not actually estimating each individual variance, but you're estimating a function of these individual variances, namely their cross product with the x variables. And that is k by k. That's not n by n. So that doesn't grow with the sample size. And as in any asymptotics, you want something that doesn't keep changing with the sample size. And that's the white solution. It's very subtle. When you look at this the first time, it seems like this problem has been solved, but in fact it's been solved, but not in the way that you think. So anytime, even with fixed effects, for example, if you see location-specific parameters, unless there is an other dimension to estimate these, say in panel data, you use the time dimension to get at location-specific fixed effects. But without that other dimension, it doesn't work. If you had a cross-sectional regression and a fixed effect constant, dummy variable, if you wish, for each observation, that's not workable, because you only have one observation for each of these. So This is not a workable model, but it's a useful point of departure. And how do we solve the problem? As usual, the same way as we dealt with the spatial weights issue and the spatial covariance issue, we impose some structure. And we can impose different types of structure. And let me backstep a second. And as I mentioned in the first class, heterogeneity is a classic problem in applied statistics and applied econometrics. What makes it spatial is that we will exploit information about the spatial structure of the data to get at this problem. So spatial means core periphery, north-south, on this side of the tracks versus that side of the tracks. So this type of additional geographic information, if you wish, and it doesn't really have to be geographic, but it has to do with the structuring of the locations in the data set, it could be a network, that is exploited to get at the problem. And we can impose discrete variation, which is in essence cuts the data set up in discrete subsets, and for each of these subsets we then have a different parameter or a different model. If you think of space-time data, each time period is a separate cross-section. You could pull them all together, and that is homogeneity, or you could cut the data set by year and have a separate cross-section for each year with a separate regression, possibly even a separate functional form, different explanatory variables, and so on. That is discrete in that you subdivide the data set in discrete subsets. Contrast to that, continuous variability. So you could say I have a parameter that varies with time, and a very simple way to implement this would be to multiply the parameter by the year. It's a very simplistic way to do this, but this then would give you a variability in that if you have a new year, you just multiply it by the parameter and you're still in business. With fixed effects, there is really no good way to deal with new observations because they don't fit into this paradigm of discrete subsets of the data. So you could have continuous variation in a systematic fashion. Typically, the cases that we will consider here are functions of other variables that we observe. And multi-level models are an example of this, and we'll go through this later on. The geographically weighted regression is another variant of this. But we can also have random variation, where we look at we conceive of the parameter as itself having a distribution. And this then starts moving us in the direction of a Bayesian approach, where everything has a distribution. So everything is random. And the issue in practice, of course, is that, as we mentioned several times before, that spatial heterogeneity and spatial autocorrelation often happen together. What are some specific techniques to deal with discrete variation? We can have what I call spatial fixed effects, and we call these regimes, spatial regimes. So spatial regimes are compact subsets of the data, compact spatial subsets of the data in which different parameters hold or different functional forms hold, and so on. The variability that we can have in there, we can think of working at a number of different levels. It can work simply at the mean level, and this is spatial analysis of variance, and we'll go over that very quickly. This is one way in which you can check whether the assumption, the stationarity assumption of a constant mean is actually maintained in the data. You cut the data up in subsets and then carry out straightforward analysis of variance, which is nothing but a dummy variable regression. And we'll see later that that can be combined with spatial lag and spatial error models. We can obviously let the error variance not be constant, that's heteroscedasticity. And more interesting, we can let the coefficients vary by regime. And so then the testable hypothesis is whether or not these coefficients are fixed. We have a model for the South, we have a model for the rest of the country. The question is, are the parameters, say, of income in each of these models the same? And obviously, They each have random variability, so we need to get at these standard errors and then combine these somehow in a test for structural stability, which in the textbooks is one of these is called a Chow test. Then when you introduce spatial autocorrelation into this, you have what I call the spatial Chow test, which is essentially the same idea, but using the proper standard errors from the spatial models in this test. So that's what we'll consider first, and then we will move on to continuous variability, which where we make a distinction between systematic variability in the sense that it is tied to other variables or to the data, and random variability, which is a different paradigm where we think of the parameters as individual parameters. So there are individual beta I, so to speak, but they're draws from a distribution. So say you posit that the slope of the income variable is not a fixed parameter, but it's a varying, a random parameter, which has a central tendency, a mean value, but variability around that mean value. And if you go even further, you can assume a specific distribution, like a Gaussian or a normal distribution, and then we're in business. Then what we will see, the main approach is to estimate the characteristics of that distribution, specifically the mean value for the coefficient, but also the variance. And then we can predict, so to speak, individual specific coefficients, which is really something that it's a very subtle difference. I mean, we are not actually estimating individual specific coefficients, but we are getting them from the characteristics of the distribution that characterizes the randomness of that random coefficient. And we'll see that later on. So these are the main, this is the main taxonomy where we distinguish between discrete variability and continuous variability. And then in each of these, we have increasingly, if you wish, more sophisticated ways or more complex ways to deal with the variability. And let's start with discrete variability and this notion of spatial regimes as it is reflected in spatial analysis of variance. And a spatial regime, as I mentioned a few minutes ago, is a systematic, spatial, compact subset of the data. And these, usually these, well, actually always, these have to be exogenous. So this is always a problem with sample selection. You don't want the sample to be selected endogenously. For example, you shouldn't pick the high-income counties and the low-income counties, and income is your dependent variable of interest. So this is, again, where a geographic criterion is very straightforward. Just like when we talked about the weights matrix, you take contiguity, there's no discussion. You come up with some fancy socioeconomic measure for distance, matters get very complicated. So typically you see in the literature in applications north-south, core periphery. Let me give you one example where it's not that straightforward. And this is some work that I did some time ago looking at deforestation in the Amazon. And there was clearly some discontinuity going on in terms of the parameters of the model, but it was very difficult to exogenously decide where the regions were, because what you could say is early deforestation and then later deforestation, but it's a model about deforestation to some extent. This boundary, this line that you draw between the two regimes is then itself the result of the deforestation process. So that way it becomes endogenous, and endogenous switching, as it's called, is much more complicated than exogenous switching. So exogenous means a priori you define the line. Endogenous means there is some other mechanism that, say, would explain whether or not a particular county has been deforested. And then after you have that, you look at some other phenomenon of interest. And this is a much more complex system to estimate, and as far as I know, there is very little to nothing in the spatial literature to deal with this. When observations are independent, it's complicated enough. When they're correlated, it is very complicated to have endogenous switching with these regimes. So the regimes, yeah.
Which publication has a discussion of this endogenous switching problem?
There is some allusion to that in a number of chapters that I've written, but as far as I know, it hasn't been worked out. I tried, but there is a paper, and I can look it up. I forgot the exact reference, but that looked at endogenous switching in a time series context. And I tried to replicate that in a spatial context, and it got way too complicated, and then I started doing something else. But yeah, it's a real challenge, and you can think of it as a mixing problem. So you have, say, different underlying distributions, and then from the data you have to determine which of the ones is actually happening in a particular location. And there is some work on this in medical statistics, in public health, in looking at possible different, in terms of rate smoothing and those kinds of approaches. You posit a couple of different regimes, if you wish, and then you let the data pick out in some kind of maximum likelihood way which one is the most likely one present in a particular observation. But as far as I remember, there is no explicit consideration of spatial correlation in that. So the fixed effects are really a fix to the structural change, but they do not explain. The other thing about fixed effects is that there's no scope for new regimes. So if you have a model for the north and the south, and now you want to model for the west, you have to start all over. Okay, you cannot get a prediction, for example, a predicted value for the west. If you can think of having a dummy variable in a model for the south and a non-south, and then if you want the west, there's no dummy variable for that, so you're stuck. So fixed effects are literally what they are. The regimes have been fixed. There is no scope for new spatial regimes. And in a lot of situations, that's a perfectly reasonable assumption to make. The question often comes up, to what extent do spatial fixed effects take care of spatial autocorrelation? And this comes up more in the panel model literature. And I thought I would mention it here, bring it up here, because there's often a confusion, and this is a classic confusion, between spatial heterogeneity and spatial correlation. And the natural reaction is, if there is some kind of spatial effect, spatial correlation, if you stick in a dummy variable for each location, you should take care of it. And in many instances in practice, that in fact does take care of it. The distinction is here between the type of spatial autocorrelation that we have. If the correlation, say, is a true cluster effect and is contained to the cluster without any spillovers, then the fixed effect will take care of it. And a lot of cluster sampling is exactly designed to deal with this. Let's say you have firms in a state, and the firms in the state are correlated because the same state policies affect all the firms in the state, and then you go to another state and they have different policies, but again, they're all affected similarly. This is often treated by using a fixed effect for the state in the firm-specific observation. Now, if there's spillover between the states, between firms in different states, this will not take care of the spatial autocorrelation. If the correlation is due to what I call apparent contagion, which is really heterogeneity, so it's a state-specific effect, then the fixed effect will take care of what looks like spatial autocorrelation. So the spatial autocorrelation would not be between the states, but it would be between the firms in the same state. And as long as the container, if you wish, that you use to set the fixed effect is the same as the range of the correlation, you have solved the problem. But it's a different problem. It's really a problem of spatial heterogeneity. It is not a problem of spatial autocorrelation. And as we saw the first day, very often these two cannot be distinguished in a cross-sectional data set. So if you would do a descriptive analysis, you would find that the firms are highly spatially correlated, because all the firms in the same state, this is this common shock idea, all the firms in the same state are affected by the same policies, unobserved, in an unobserved fashion, so it's in the error term, and they all share the same factor, so to speak, and that gives them the spatial correlation. But it's not really, it's constrained to the state, it doesn't spill over to the next state, so then a dummy variable or some other way of treating heterogeneity is fine. But it is not true, it's not correct, that using fixed effects, spatial fixed effects, corrects spatial autocorrelation. If the autocorrelation is of a more general nature and actually spills over across the states, this will not fix the problem. So in general, if the range of interaction is contained fully within the regimes, then a spatial fixed effects approach will in fact correct for spatial autocorrelation. But this is not a general conclusion. So let's move on to spatial analysis of variance, which is focused on variability in the mean. And basically what we're interested in here is whether the mean effect, say crime rate or disease rate, is in fact constant throughout space. So the alternative hypothesis is that it is not constant. So each sub-region, if you wish, has its own crime rate or its own employment rate, which is significantly different from the unemployment rate or crime rate in the other region. So the null is equality, the alternative is difference. This is very standard stuff. The difference, there's two differences here. One is that the definition of the regimes is based on spatial criteria. And the second one is that because of this cross-sectional data that we carry this analysis out on, there is a possibility of spatial correlation in the form of spatial error and spatial lag. So then we can enhance, if you wish, a standard spatial analysis of variance with these spatial models for spatial autocorrelation. So we can run them as a spatial lag and run them as a spatial error model. What is this going to do? For the spatial error model, it's going to affect the standard errors, which will affect what is in a classic textbook case a t-test. We're comparing means in subsets of the sample. That's a t-test type of thing. This is just a complicated way of doing a t-test as a dummy variable regression. But if there is spatial autocorrelation in the error terms, the standard errors of a straight OLS regression will not be correct. So we're correcting the standard errors in the spatial analysis of variance, which may affect the results of our hypothesis test. So say we could be a case that in using OLS results, we do not reject a null. Using the spatial error model, we do reject a null, or vice versa. The spatial lag interpretation is a little trickier. There isn't really any reasonable model for spatial interaction here, or some substantive model of spatial competition. It's simply comparison of means. But you can think of it as this spatial filtering problem. So there is a problem with the scale of the data, and by filtering out the spatial autocorrelation by means of a spatial lag model, we get the proper estimates for, in this case, the dummy variable coefficients, which then allow us to do the proper comparison of the means between the subsets. So in both cases, the spatial autocorrelation affects the properties of the estimates in the standard dummy variable regression that you use to carry out analysis of variance. So this, you might see in the literature, is referred to as spatial analysis of variance. It's really not that complicated. It's simply taking care of problems of spatial autocorrelation that are present in the data to get the proper standard error and to get the proper estimates. Because remember, if the spatial lag is the correct model, and if you do not include the lag in the model, then the estimates of the parameters are inconsistent. And so what this really means is that the estimates of these mean effects are inconsistent if you have an ignored lag. And in some cases, it does make a difference. So the way this is implemented is very simply, if you have no constant term, then you regress the dependent variable. There's only really one variable of interest here. You regress the dependent variable on dummy variables. One is 1 for one region, the other one is 1 for the other region, and then 0 otherwise. Now, in that case, you can test a null hypothesis of the betas, which are the dummy variable coefficients, being equal. And that's very straightforward. In practice, very often it's put slightly differently in that there is a constant included in the regression, and then the beta parameter is a test on the difference from the overall mean. And again, this is very easy to do. You correct for spatial effects if appropriate. And I wanted to illustrate this with the example of the South. And we start with a simple, and this is also in the workbook, the R workbook that we'll look at this afternoon in the demos. This is a straightforward regression of homicide rate. Using the whole country. Yesterday in the lab you used the South only, but if you use the whole country and put in a dummy variable for the South, you see it's highly significant. And so the interpretation of this is how much different the homicide rate is in the southern counties relative to the nation as a whole. As we look at the diagnostics in this particular case, we see, first of all, let me step back a second, and you look at the R square. It's not a disaster, but it's not terribly good either, as you would expect. There's really not much in there in terms of a model, but it's amazing that just a dummy variable for the South explains 1/5 of the variance, just that alone. It doesn't explain anything, but it picks up 1/5 of the variance. So then it's no surprise that there is a ton of spatial autocorrelation here. This is again one of these tricky cases where it is all over, and it's very difficult to actually distinguish a lag from an error model, but then that's no surprise because basically we just have one dummy variable and the rest is just error terms bouncing around. So there is a slide edge, if you wish, for the lag model, but I wouldn't make too much of it in this particular case. What you then do is run a spatial lag model, and you see that indeed the spatial autoregressive coefficient is actually quite high, 0.38. And what it does, it decreases the value of the differential of the South. So it affects the estimate of our differential between the overall, the grand mean, as we say, and then the South itself. So after correcting for the spatial lag effect, after filtering out the potentially biasing effect of spatial autocorrelation, we come up with a much smaller differential, but it's still highly significant. Okay, so in the end, the substantive interpretation is the same. I have seen cases and other situations where this is not the case, so that the inference actually changes after filtering out the spatial lag. And
the spatial lag is not in some way included the information about the north and the south, because it's in the weight matrix we have this information about the neighbors. Or, why do we keep the dummy? I understand we keep the dummy to differentiate south and north, but the the weight matrix is not in some way including that information also?
There are really two things going on. The one is the spatial process that drives the spatial autocorrelation, and that goes on throughout the whole data set. And then after you have that, you can think of it that way, after you have that and taken that out, is there still structural change between the two areas? Okay. So, I mean, if you made your weights matrix that there were block diagonal, then you would in fact do the same thing twice. Okay. But this is a very subtle difference. It's actually not that subtle because it has to do with the asymptotics. You know, the spatial processes are all based on the n going to infinity. And we saw yesterday you can go outwards, expanding domain, or you can fill in, infill asymptotics. So when you have two subsets in the data, when you have two regimes, the question always arises, do these each have their own asymptotics, or is it one for the whole data set? And the argument for the asymptotics by regimes works very well in a panel data set. Say you have a cross-section in 1 year, a cross-section in another year. You can think of each of these cross-sections, especially if they're the same, say the same counties or the same states, as having their own asymptotics in the cross-sectional domain. But if you take the country and cut it into north and south, then you would have to start thinking, is there a way, and you know, as I said yesterday, this is not a practical thinking, this is a conceptual. Is there a way in which we can think of asymptotics separately for the south and separately for the north? And if there is, then you can separate the spatial processes for the two. But usually that's kind of hard to think of, and then the spatial process, like the lag model, the autoregressive model, or the error model, works for the whole data set. And then you can think of it as really, you can think of it as a two-stage process. It's not actually implemented that way, but whereas first you take care of the spatial autocorrelation, and then on what's left, you check for the structural variability.
This is a question for me. How do you decide how do you compose the regime? What constitutes the regime? So here you made a, for the global structure, you made a slice south and rest. But you could, we tried like census districts, the 10 things, and similar kind of results. But you know, we never knew what constituted the regime. We didn't want to, if you slice it fine enough, you're down to the local level. And so Moran's at local levels. You're just being redundant. And I don't know what collinearity would be here, but there it's got to be very high. So how do you decide how to constitute this compact subset, this regime? Do you have a guidance on? You just try a bunch of things?
I don't really, the question is about how you constitute the regimes. And it's really problem specific. And if you're lucky, you have some exogenous institutional factor that determines the regimes. For example, some law that has a clear geographic content, or a language, or if there is a religion difference that's clearly spatially separated, those types of things. Where it gets tricky is, like in my example of the Amazon, where the actual regime definition is part of the process that you're trying to model. And the answer there, and it's been intriguing me for a long time, is to deal with this endogenous switching. You know, so that you have a model, in a sense, for the membership of the regime. What is the probability that the unit that you observe is part of the regime? And then, given that, you model whatever it is that you're interested in. So it's like a two-step process. But that's very hard to do with spatial autocorrelation.
Is it valid to about setting up the regimes exogenously, as you would say, for instance, in policy, different policies applying to different states. But then if you actually have lower order observations, more local observations of the heterogeneity in response to that regime, can you still include that as a separate variable, which really is at a different hierarchical scale?
So you really, yeah,
so
you're,
it's sort of like you're getting at it, the exogenous variable at one slice in terms of partitioning the space, but then again, you have another variation of that exogenous variable that's explanatory at a local scale. Does that make sense?
well, it's really about a mixing of scales, right? You have local observation and then higher order observations. And I think when we talk about multi-level modeling later on, this is another way of dealing with heterogeneity. And it's kind of a mixture of discrete and continuous, because you will each of the regimes, so to speak, has its own parameter, but then the variability between the parameters is modeled in a continuous fashion. So you have kind of a varying coefficient where the variability is driven by the differences between the regimes. But you still have the same problem of defining the regimes. And in multi-level modeling, in most applications, the problem itself dictates the solution. So you do, kids in a class, then the school becomes the next level, and maybe the school district becomes the next level. Those are all exogenously defined. If we do spatial regimes, it's a lot trickier, because if we say, well, which county belongs to the south? I recently saw a very interesting paper where the southernness of counties in Texas was looked at in terms of how they voted. And forgot which election it was, 68, I think, and how they voted. And in fact, it turned out that some counties were much more aligned with the South than others that were much more aligned with the rest of the country. And so then this is where the endogenous switching becomes more interesting. And why is it that these counties belong to this regime rather than the other regime? And this is something that is kind of a common thread through all this discussion, is that a lot of these particular techniques are fixes. They don't explain. And they're only as good a fix as the strength that we have to determine these regimes exogenously. And when that's really one of the things you end up with when you draw the line yourself. For example, if you define in the Amazon, here's the line, this is early deforestation, this is late deforestation. What happens if you move the line a little bit? And that's where you get into the problems you mentioned. Okay, heteroscedasticity is a straightforward problem. Again, here the complication is that this group-wise heteroscedasticity, meaning different variances in the different regimes, occurs together with the spatial correlation. And then you model, as I alluded to yesterday, when we did the maximum likelihood write-up, we assumed no heteroscedasticity. It's actually fairly straightforward to add group-wise heteroscedasticity to that model. You just have separate variance terms for each of the regimes, so to speak. Okay. Spatial regime regression is moving up a little bit in terms of complexity, but it's very much the same frame of mind. But now we let not only the mean vary between the regimes, but we let the parameters themselves. So we have, let's say, two subregions, region 1 and region 2. In region 1, the parameters are alpha 1, beta 1, and in region 2, the parameters are alpha 2 and beta 2. So then the question at hand, the hypothesis is, are these truly different? And do the data let us distinguish between the two subregions in terms of the parameters of the model? In other words, is the slope in region 1 the same as the slope in region 2? And that's a very standard question in terms of regional homogeneity. So you have two, say, labor demand functions. You estimate one for the south and one for the non-south. are these parameters the same in the two regions, or are they different? Then, of course, if they are different, it doesn't actually explain that they are different, but it tells you that this is something to think about. And this is important, again, for policy analysis. We talked a little bit about this the first day, this heterogeneity, because if indeed the responses, say, to a particular incentive, or to a tax incentive, or to a training incentive, are different in different subsets of the data, in different subregions of the data, then the policies should be in tune with that. And say, what we often see when we do these regressions is that in some parts, in subsets of the data, the slope is not significant, and in others it is. And so you can think of this as nonlinearity of some form. If you have a regression, a linear regression, you assume linearity, but what if the slope, say, if it depends on income? And with low-income people, there's a high response. High-income people, there's no response. But you fit a single linear regression, so they all get thrown together, and you get some kind of an average that responds to neither group. Just transpose this in a spatial setting and think of no response in part of the country and another high response in another part of the country. You apply a common slope to this, and you get some average that really doesn't exist anywhere in the country. So that is the main reason for assessing this. And so the working hypothesis is always constancy, is equality of the coefficient. And that is a testable hypothesis. What you do is you compare the separate coefficients to a pooled model where you throw everything together. So the tests then are, as I mentioned, we can have a number of different combinations equal. Did you have a question?
It seems like one possible problem you spoke on the previous slide, the two equations, is that what if you expect the error terms to be related across these two regimes, that you left out the same set of variables?
Yes, that's exactly what we do with the spatial test for structural stability. So it's again the same approach as with the spatial analysis of variance. You have the two regimes, but the error terms share a common spatial process throughout. So then in the modeling, you take care of that first. In some sense, you take that out of the problem and then redo the test. So the spatial tests for structural stability use the proper standard errors after you do a spatial lag or a spatial error regression. Okay, but that's right. I mean, it's like in time series. If you have a structural break and you have some kind of autocorrelation process, why would that all of a sudden stop? At the structural break. And it's the same way in space. If you have a spatial autoregressive process, say, why would it stop at the boundary between two spatial regimes? It could, if there are islands, for example, or if there are other good reasons to think about it that way. But typically, there is no good reason to think about it that way, and we really need to let the process proceed. So the tests, obviously, you can do all kinds of combinations, slopes only, intercept and slope, only some variables, all the variables. And the way we progress with this is we carry out regressions for each of the regions, but we stack them so that, in essence, we throw them together, and then we can allow the U1 and the U2 to either have the same variance or different variances, but we pool them, but we don't force the equality. The equality of the parameters is a testable hypothesis. And so, for all practical purposes, this is the same as running the regression separately. But in terms of the implementation of the test, it's an easier way to think about it, because now what we're testing is to know that beta 1 equals beta 2. And this is a simple test within a standard regression framework. Of course, this is based on standard errors, and this is where the spatial effects come in. What are the proper standard errors? If you have a spatial error process, you have to adjust them. If you have a spatial lag, you have to adjust them And that's, in a nutshell, what this is about. So this is an example. Again, we'll see this in the lab later on as well, where we now run separate regressions, but we run them together. So we have the data set for the whole US. We have created a separate X matrix for the South and for the non-South, and we stack them with these off-diagonal elements being 0. So there is no crossover. There's no southern county that enters in the non-South regression and vice versa. Then each of these has its own set of parameters. So if you look, for example, at the coefficient in the bottom, the unemployment coefficient, in the South it's negative and highly significant. In the non-South, it's slightly positive but only marginally significant. And that is the kind of information that you get. There is another one. If you look at the PS, which is population structure, right? I always forget what these are. PS is another clear example of, in the non-South, they're both positive, but in the non-South it's highly significant, and in the South it's 0.07. So that is, basically not significant. And so these are the kinds of things that you look for in these spatial regime regressions. And then, now how do we test this? Formally, there is a classic test called a Chow test, which is a test on structural breaks. Originally, that's where it came from, but you can apply it equally well in a cross-sectional setup. So we, in essence, compare the residual sum of squares in the constrained regression versus the unconstrained regression. And the constrained is just like yesterday. The constraint was setting the parameters to a certain value. Yesterday we were setting it to 0. Now we are forcing them to be the same. So the constrained regression is the one where beta 1 and beta 2 are the same. They are constrained to be equal. The unconstrained regression is the one where we allow them to be separate. And the rationale here is that if they're truly separate, then we should see a significant difference between the fit in the two regressions. Then the one with no constraint should fit the data much better than the one where we force them to be the same. And that's in essence what the test is about. It's in every textbook. Now what we do is make this a spatial test, and this is a same idea. It's a test on the coefficient equality, but now we can do this based on the results of a spatial error regression or a spatial lag regression. For example, in a spatial error regression, we look at the test after some algebra becomes a difference in not anymore between the straight residual sum of squares, but between the spatially filtered or the spatially weighted residual sums of squares. So this requires a spatial error estimation in the unconstrained model, which gives us a different beta in each region, and a spatial error regression in the constrained model, which gives us the same beta in each region. Each of these gives us a residual vector. It gives us a lambda. We stick the lambda in here, and that's a spatial Chow test. And similarly, for the spatial lag model, we can do something where we take the likelihood of the models. Let's see. Yeah. It's on the top here, the yellow part, and we carry out a simple likelihood ratio test. In essence, this is comparing, again, the fit of the model with the constraint imposed and without the constraint imposed. And so if the constraint is valid, then the fit between these two should not be very different. And it's the same as what we did yesterday. What is not very different, that depends on the standard errors. And so once we have those, we can carry out this test. So it's actually a straightforward thing to do, as long as, of course, you estimate these models as a lag model or as a spatial error model. And then in our example, if we take, for example, the spatial lag specification, then we see that there is a strong rejection of the null of equality of the coefficients. And you can do this for all the coefficients jointly, or you can do it specifically to, you know, one or two of these coefficients, and then you can have a mix of a model with some parameters being constant throughout the whole data set and then some being different. As I mentioned in the beginning, this fixes the problem, it doesn't explain anything. And the question still remains then, why is it that unemployment in the South matters, but it doesn't matter in other parts of the country? And so that's the challenge with spatial heterogeneity.